So, what is the simplest example of equivalence relation on a non-empty set? So, for example, A be a non-empty set, then we define R on A as what? A relation on a set. Okay, on a set. It should be on the same set. So a relation define R on A as what? Say x comma y belongs to R if and only if. So if and only if has got a short form that is called I double F. Okay. This means if and only if. Okay. X y will be related if this happens, and if x y is related, then that will happen. Okay. That is called if and only. Both ways. So define R on. So what is the most obvious equivalence relation? From the name itself, you can say. I don't know what is this set. I do not know what is this set. It is any set. Okay, any non-empty set. So what is the most obvious equivalence relation? एकदम simple. No, I have to define some criteria under which x, y belongs to R. Okay. X and y will be related if something happens. What should happen? X equal to y. एकदम simplest equivalence relation. Okay. So x and y are related only if they are equal. Okay. So this is the equivalence relation, right? So under this relation, so this is reflexive. Why? Because x is always equal to x. You take any element, it is always equal to it. It is symmetric because x equal to y implies y equal to x. It's the same thing. We are just writing it in a different order. Third time transitive because x equal to y and y equal to z means x is same as z. Okay. So this is just equality. Nothing else. So under this relation only this type of elements will be there. Okay. Say 1, 1, 2, 2, 3, 3 like that. Okay. Those type of elements will be there. So this is the most obvious equivalence relation on any set. Okay. So we can have at least one equivalence relation in every set. Okay. At least একটা equivalence relation থাকবে. So some more examples are this. Another example we have already done that. This one. Let z be the set of integers. With a set of integers we define. So this is called congruence modulo. Okay, congruence modulo n. Okay, say or suppose let us start with 5. Let z be the set of integers, and we define R on Z as a comma b belongs to R if and only if 5 divides a minus b. Okay. 5 divides a minus b. This is actually 5 divides a minus b. Okay. So we have not done this. We will do this. Z be the set of integers, and we define a relation R on Z as a and b are related if and only if a minus b is divisible by 5. Okay. So tell me some elements in this relation. A minus b is divisible by 5. What are the elements? 5 0 is an element there because 5 minus 0 is divisible by 5. Okay. Another element 6 comma 1. Okay. This is also an here also 6 minus 1 is 5 is divisible. 6 is also related to minus 4 because 6 minus 4 will be 10 and 10 is divisible by 5. Okay. So 6 is also related to minus 4 like that. So these are some elements inside this relation. Okay, so this relation is actually called congruence modulo 5. This R is actually written as this way. A is congruent to B modulo 5. Okay. Right, A congruent to B modulo 5. So that is the meaning of this is 5 divides A minus B. Okay. So I think this was there in your advanced mathematics. Advanced mathematics se wise. Recently it was included, number theory, in the advanced mathematics course. Okay. If A and B are, so this is a very important part of number theory. Most of the Olympiad problems and all, they are solved using this. Okay, so how to show that this relation is equivalence relation? Okay. So first I have to show that R is reflexive. So how do you show? Let A belongs to Z, be any element. I have to show that A is related to itself. Okay. Be any element. Then, so if A is related to itself, what should happen? A minus A should be divisible by 5. Okay. What is A minus A? A minus A is 0. Okay, and we know that 5 divides 0. Okay. 5 divides 0 because 0 is divisible by any non-zero number. 0 can be written as 5 into 0. Okay. Right, what is the meaning of A divides B? A divides B means again? B can be written as A into some integer. Okay, some integer. Right. A divides B means B can be written as A into K, where K is an integer. Okay. K is an integer. Right. So suppose 4 divides minus 12. Why? Because minus 12 can be written as 4 into minus 3. Okay. Huh?
5 by 0.
5 by 0. This symbol is not this. Okay. It is straight symbol, bar. Okay. So this symbol means A bar B. This means A divides. Okay. It is not A divided by B. Okay. A divided by B, something like this. Okay. If it is a slash, then it is A divided by B. Okay. That is a rational number. Here it is not a rational number. Here this means that A divides B. Mane A B रे divide करे. Okay. A divides B. Or equivalently, B is divisible by A. Okay. So this symbol means this. You can always all of you can write it somewhere. Okay. A divides B mane this A bar B. This means A divides B. That is B is divisible by A. Okay. So 5 divides 0. Okay. Whenever I write 5 slash 0, A slash a bar okay. Don't write something like this. This will mean that 510. Okay. So always write it like a large one. Okay. 5 divides 0. So here A minus A is 0. And 5 always divides 0. Okay. So therefore, A is related to itself. A comma A belongs to. Okay. So R is reflexive. Right. Next is R is symmetric. R is symmetric. So for symmetric, I have to show that if AB belongs to R, then B also should belong to R. Okay. So let AB belongs to R. Then what happens? Then as per the definition, 5 divides A minus B. 5 divides A minus B. That means what? A minus B can be written as 5 into K, where or 5 into K, where K belongs to integers. Okay. This is the meaning of 5 divides A minus B. So that means if I change the order, B minus A will be what? Minus 5K. Okay. B minus A is same as minus 5K. So I can write B minus A as here I can write b minus a as 5 into what? Minus a. Okay. Minus 5k can be written as 5 into minus k. No? So that means b minus a is also something like 5 into some integer. Okay. So this means that 5 divides b minus. Okay. So these are actually properties of divisibility. So it is also there in this paper only. Okay, we will do that. So b minus a can be written as 5 divides b minus a. So as per the definition, b comma a belongs to this relation R. Okay. So R is symmetric. Right. Therefore R is symmetric. Okay. Clear. Then next is R is transitive. R is a transitive relation. So how to show R is transitive? So for transitive, I have to start with 3 elements which are related. First is related to second is related to third. Okay. So let AB, BC belongs to R. Okay. Let AB, BC belongs to R. Okay. Then what can I write? 5 divides A minus B. And 5 also divides B minus C. Okay. So again I can apply property of divisibility, but let me do it in 2 steps. So 5 divides A minus B. The meaning is A minus B can be written as say 5 into some K1, and B minus C can be written as 5 into K2. Okay. Where what are this K1 and K2? K1 and K2 they are integers. Okay. Belongs to Z. Okay. The set of integers. They belong to Z. So if I add them, I want the relation between A and C. Okay. So if you add them, what happens? So add for. Therefore A minus B plus B minus C is equal to what? 5 into K1 plus. So this means that A minus C can be written as 5 into some integer. K1 plus K2, where K1 plus K2 is an integer. Okay. Sum of 2 integers is an integer. So from here I can write 5 divides A minus C. Okay. So that means AC is an element inside this relation. AC belongs to R. So R is transitive also. Okay. So R is reflexive, symmetric as well as transitive. So it's an equivalence relation. Clear? This is an equivalence relation. Okay. So maybe sometimes the symbols are changed. So in exam maybe if the question comes like this, we define a relation, instead of R this may be congruence. Okay. So don't get confused. We define a relation this on Z as A congruent to B. Okay. Mod 5 if and only if 5 divides A minus B. Okay. So if it's something like this also, no problem. The proof is exactly the same. Okay. Let A congruent, instead of writing AB belongs to R, just write let A congruent to B. Okay. Then you show that B is congruent to A. Okay. So don't get confused. So you can do it in general. Congruence modulo n. Okay. Modulo n. Okay. Let Z be the set of integers, and we define R on Z as AB belongs to R, if and only if AB belongs to R, if and only if this happens. N divides A minus B. Let Z be the set of integers, and N belongs to natural number. Be fixed. Okay, this is a fixed natural number. So this is your next example. Congruence modulo N. let Z be the set of integers, and we define and n belongs to natural number be fixed. Okay, full stop. After that we define. Okay, after this we define R on Z as a comma b belongs to R if and only if n divides a minus b. Okay. Right. Then R is an equivalence relation. Okay. Then R is an equivalence relation. Equivalence relation. Okay. Exactly same. Instead of 5, just it will be n. Okay, nothing else. What do you do? Huh? Instead of 5, you just have to write n. Okay. You do it. Okay, you do it yourself. So another example of congruence equivalence relation you can give. So this also you try proving it yourself. Let S be the set of all straight lines on a fixed plane. Define R on S as a comma b, or say x comma y belongs to R if and only if x is parallel to y. Show that R is an equivalence relation. Show that R is an equivalence relation. Okay, so here we adopt the convention that the convention is, we adopt one convention is a line is parallel to itself. Okay, line is parallel to itself. Okay, we adopt this convention. So sometimes if the lines are coincident, because somebody may say no, they intersect, so they cannot be parallel. They are actually parallel. Coincidence lines are actually regarded as parallel. So you try to show it. Very simple. X is parallel to itself, so it's reflexive. If x parallel to y, y is parallel to x. Okay, geometrical definition. And then if x is parallel to y, y is parallel to z, then we can write they are parallel to z. Okay, so just you have to write the. Okay. This is also equivalence relation. Let us try this exercise. Let A be a fixed set, okay, or given set. Let A be a given set, and PA is the power set of it. The power set of define a relation R on PA on the power set of A as x related to y. Xy belongs to R, that is x related to y if and only if x is a subset of y. Is it reflexive, symmetric? Check if it is reflexive. Check if it is reflexive, symmetric or transitive. There we go. X and y are related if so. Here x and y, they are all subsets. X and y are elements of the power set. Okay. Power set means the set of all subsets. Okay. So is it reflexive? Reflexive way. Can I write x is a subset of x? Every set is a subset of itself. Okay. These are elementary set theory. So this relation is reflexive. Is it symmetric? It's not symmetric. if x is a subset of y cannot be a subset of x. Okay. Y is a superset of x. Okay. So you have to give one example. Okay. Suppose you take one element A inside capital A, then singleton A, and you take two elements. Okay. A B belongs to A comma B belongs to A. Okay. So singleton A is a subset of AB, but the other way it is not true. AB is not a subset of A. And it is transitive, no problem. X is a subset of y is a subset of z. So this is a subset of x is a subset of z. Okay. So it is reflexive, transitive, but not symmetric. It is not symmetric. Okay. So your task is to complete this also. You complete this. Okay. So there are lots of problems. It's not necessary that whatever I do in class will come in exam. So you should do these things. Okay. Next is okay. So try this. Let A equal to the set 1, 2, 3, 4. Which of the following are equivalence relations? Which of the following are equivalence relations? Equivalence relations. Number one is they are equal to 1, 1, 2, 2, 3, 3, 4, 4. Number 2, 1, 1, 2, 2, 3, 3, 4, 4, 1, 2, 1, 3. Number 3 is r equals to 1, 1, 2, 2, 3, 3, 2, 3, 3, 2. Now tell me, which one is equivalence relation, or which of these? Number 1, is it equivalence?
Yes, sir.
It is reflexive. Okay. It is symmetric also. If you take an element of the form AB, BA is also, suppose 1, 1, it is there in R. 1, 1 is again there in R. Okay. So you don't have these elements of the form AB where A and B are different. Okay. So our work is much simpler. So this is always reflexive, symmetric. It is transitive also. Okay. You cannot find elements of the type AB, BC where AC is not there. Okay. So here, see 1, 1. Nothing else starts with 1. Okay. So similarly 2, 2. So nothing else starts with 2. Okay. So this is the same thing. So this relation is actually that x equal to y. Okay. A and B are related if and only if A and B are equal. Okay. That relation is this. So this is actually this equivalence relation. This one?
No.
It is not equivalence. Why? It is not symmetric. 1, 2 is an element inside this relation, but 2, 1 is not there. Okay. So how will you write? R is not R is not equivalence relation as R is not symmetric. R is not symmetric. Okay. If any of this is not satisfied, then it is not equivalence relation. Okay. For equivalence, everything has to be satisfied. Reflexive, symmetric, transitive. So if at least one of these is not satisfied, it is not equivalence. So as R is not symmetric. Why? Why it is not symmetric? 1, 2 belongs to R, but 2, 1 doesn't belong. Okay, doesn't belong to R. Okay, so you have to justify it that way. Next, number 3. 1 2 2 2 3 3 2 3 3 2. Equivalence or what? No, it's not equivalence. Why? 4 comma 4 doesn't belong. It's not reflexive. Okay. It is not a reflexive relation. Okay. So it's not equivalent as R is not reflexive. Not reflexive. Okay. Why it is not reflexive? Because 4 is not related to itself. Okay. For reflexive, every element should be related to itself. Okay. This one?
No.
It is reflexive, no problem. It is symmetric, but it is not transitive. Why? 1 3 is an element, 3 2 is an element, but 1 2 is not an element. Okay, clear? 1 3 ase, 3 2 ase, but 1 2 is not there. Okay, so you have to observe very carefully. This is not transitive. Okay, this is not reflexive. That was not symmetric. So here R is not transitive. Not transitive. Okay. So that is why you have to understand. Okay. We can create thousands of examples like that. So you have to, if you by heart, you will not be able to understand, or you will not be able to answer. Okay, you have to understand the concept. এখানে 1 3 আছে 3 1 আছে 1 1 আছে নি ওটা দেখো 1 1 is there, 1 3 is there, 3 2 is there, 1 2 is not there. Okay, so it's not transitive. Clear? Similarly, this one also 2 3 is there, 3 1 is there, but 2 1 is not there. Okay, so it's not transitive. Clear? So next, we have a concept called equivalence class. So let me see some more examples. Equivalence relation. Okay, you try this one. Yes. Consider the relation R on the set of real numbers. Okay, on R defined as, so these two R's are different. This is the set of real numbers, and this is the relation defined as R equal to the set of all those xy inside such that x into y is strictly greater than 0. X into y is strictly greater than 0. So is it an equivalence relation? Is R an equivalence relation? Equivalence relation. So track x into y is greater than 0. If that happens, then they are related. Is it an equivalence relation? No. Why? Not reflexive. If x is 0 into 0 is not greater than 0. So 0 is not related to itself. Okay, so it's not reflexive. Okay, for every other element, if you take x to be non-zero, it is always true. X is always related to itself. Only the element 0 is not related to itself. Okay. So it's not reflexive. So we can make it reflexive by including this 0 0. 0 is related to itself. I have included it separately. Now try whether it is reflexive equivalence or not. We have included 0 0. 0 is related to itself. Separately we have included. Yeah. The relation is actually a set. It is a subset of across it. Okay. So it is a subset of R cross R. Okay. So with the relation, I can take this union. So union of two relations on a set is also a relation. Intersection of two relations, that is also a relation.
एक अगर माइनस हो गया एक प्लस हो गया तो
Done.
X positive है।
তার হচ্ছে এই যে এটা নোটিস মানে গ্রুপের এটা তোমরা এটা ট্রাই করো।